So like I said, yeah, we're going to do just chronologically chapters 1 through 6. So, and I try to pick out the stuff that I think is important, that was really like, important in upcoming chapters and whatnot that we use. So that's what we're going to kind of go over. So for chapter 1, we talked a lot about the different types of variables that we have. And then, so remember that we have sample statistics and population parameters. These words always go together. You're never going to have a sample parameter or population statistic. Those aren't things. Sometimes people get those messed up. Remember, this is like the biggest thing every semester I see people mess up, and it's a simple thing that you guys can definitely understand. It's just, these are the symbols that you use for sample statistics, and these are the symbols used for population parameters. Okay, so if you're talking about a population proportion, you're always going to use P. You're not going to use P hat. That's not going to happen. So this is just something to keep in mind. Like when you're writing out hypothesis tests, your null and alternative hypotheses are always going to be written with either mu or P. Okay, you're never going to have something else going on there. That's just not how it is. So yeah, these are just things to keep in mind. Sometimes I, tell people to write these out so you remember that, just, and also so you understand, if you see X bar, they're talking about a sample mean and not a population mean, that kind of thing. So, but just remember, random variables, they do vary, and then populations are going to be fixed. Sometimes I draw the little umbrella thing that people tell me looks like a pie, but I don't care. I'm not as every professor says, I'm not an artist, but I'm going to draw it on the board. Okay, so this is your population, and then you take a bunch of samples out of it, which are your little raindrops out here. So we got our samples, and you want these to be randomized in order for them to be representative. And then I always draw it in aspects of this. So you take your samples from the population, and your samples are used to make an inference about the population. So because samples are easier to analyze than the entire population, so that's why you're using these to make an inference about the population. And that's why you want the samples to be representative of our population. So amazing, cool. So yeah, that's just something that's like the basis. But remember, like, these symbols, they're very important. Okay, so we have explanatory variables and response variables. We have our explanatory variable, which is independent. It explains the difference in our response variable, which is the outcome variable that is dependent upon the explanatory variable. And in terms of if you write this on a distribution, our explanatory variable is always going to be on the x-axis, and then our response variable is always going to be on the y-axis. So, and I always remember it like explanatory has x, explanatory. So that's something to keep in mind. That's something that's easily messed up. So if you think about it, whatever happens down here on the x-axis, whenever you're plotting points, you figure out where it is on the x-axis, and then depending on where that is, that'll decide where it is on, the y-axis and what the response would be. So remember, this is dependent upon the explanatory variable, which is independent. So yeah, variables, they're variable. All right, so just a few other things about independent and dependent variables. So independent means that they're unrelated. They don't affect each other. This is they're saying the same thing. And then if it's dependent, they do affect each other. So if something happens to one, it's going to affect the other one. Paired and matched pairs, talking about these, this is saying that when they're dependent on one another, and it says many times subjects are the same in both groups. This is something if we have, like students 1, 2, 3, 4, etc., and we have like their lab 1 score, and then we have like the quiz 1 score, and then we wanted to compare for each student. This is showing that the subject is going to be the same in each one, because you're going to have, this is both for subject 1, but the pairs between lab 1 and quiz 1, and you're trying to see if they affect each other and in what way. So they're dependent upon one another because you're predicting that someone's lab 1 score, impacts their quiz 1 score or something like that. So that's what we mean by it might be the same subject in both groups there. Okay. All right, chapters 2 and 3, which we're talking about describing data. So when we're describing data, we can talk about either categorical variables or quantitative, so categorical. Cat is an animal, so animals are an example of categorical variables. And they would also be nominal because they don't have any order. So these could be things like colors, brands of something, like material types, anything that basically is only a category, doesn't have a numerical value associated with it. And then ordinal are the same thing. They're still labels. They don't have any numerical value, except they do have some sort of hierarchy to them. So you can have like bronze, silver, gold, forgot the D in there, gold, bronze, silver, and then gold. That's an example of an ordinal categorical variable. There's still categories, but there is some sort of hierarchy. Same thing with like freshman, sophomore, so on and so forth. That's going to be categorical ordinal because there is a hierarchy to class standings. Quantitative have a numerical value, and discrete means they can only take on a certain set of numbers between the max and the min. This is often like people, things that you can't split up, so it can only have like whole numbers. Continuous are things like measurements, and in terms of like, I guess you could like any type of like weight or height, inches, centimeters, so on and so forth. So these once again have some sort of numerical value associated with them, but they either can only take on a set number of values, or they can go on and on and have decimals and whatnot. So those are our types of variables. So we have our quantitative data display. So our box plot, histogram, and dot plot, these are going to be the ones represented right over here. We'll talk about scatter plots in a second, but these are ways you can represent quantitative data. Our box plot is the one that we can kind of talk about our quartiles in. So if we draw it out down here as an example, just remember what is shown on here. So remember, we have our minimum. Down at the bottom, we have our maximum. We also can have like outliers on some of these sides. And then remember, we do have our quartiles here. So Q1, Q2, Q3. Q2 is always going to be our median. And then if we're talking about percentiles, it's going to be our 25th percentile, 50th percentile, and then 75th percentile for Q3. And the percentiles are just saying what percent of the data lies at or below that value. And then do remember that the IQR is going to be this area in here. And also the box does complete the middle 50% of the data. So you have 25% over here, 25% there. But don't let that get you messed up in terms of the percentile. So if we're talking about the 25th percentile, that means that at Q1 or below, so all this stuff, this is going to be 25% of the data that lies there. That's what the 25th percentile means in terms of that. All right, so then, and histograms and dot plots are similar, except for histograms are used more for larger data sets. And then because you can make these, the x-axis or the y-axis, like however much you want, for dot plots, you put each singular thing. So if you have like 1,000 points at one of these, you don't want to be putting 1,000 dots unless you have a lot of time on your hands. So yeah, that's like an advantage of having a histogram, because you can use it for larger data sets. Okay, so this is going to be talking about scatter plots. So once again, these are for quantitative variables, but they are going to be for 2 of them instead of just 1. So we have 4 different things that we talk about in terms of scatter plots. So we have our direction, which is positive or negative. So if we look at this example here on the side, I'm going to say that this one's negative because going from left to right, it's going in a downward motion. So I'd say this one's negative. Form is going to be linear, nonlinear. This one looks like a line to me. So anything that if you saw would be like something googly like that, or like if you saw like a parabola or something, those ones are going to be nonlinear. But we do want it to be linear, so that is something we want to keep in mind if we end up making conclusions about it. Our strength is going to be weak, moderate, or strong, depending on how close the dots are together. This one I'd probably say, and you can also kind of like combine them, it's kind of like moderately strong. I'd say it's getting pretty close to being strong together. The dots are pretty close together. And outliers, I don't really see any here, but if I were to put like a value over here, that'd be an outlier, something that's like super far off from like any point that's there. And once again, here we have our explanatory and response variable, as we talked about earlier, on our x-axis here for explanatory, and then y-axis is our response variable. All right. So then, oh yeah, and this is just a reminder of the different shapes that we can have our data in, skewed to the left, skewed to the right, and symmetrical. And then in terms, like, what does that mean in terms of our mean, median, and mode? Our median's always going to be in the middle, no matter what. But the difference is for skewed to the left, our mode is going to be on the right, the most commonly occurring value, while in skewed to the right, our most commonly occurring value is going to be on the left, and our mean is going to be wherever the most spread is, which makes sense because that's like the most value. So our mean is going to be on whatever side that is. So left for left skew, right for right skew. Symmetrical mean equals median, which equals mode. Kind of makes sense in that aspect. All right. Okay, so these are categorical data displays. So same idea in terms of displaying data, but this is going to be for categories, not numerical values. So the bar graphs are showing you the frequency of different categories here. So you have your categories on the x-axis, and then the frequency of them, or what you're measuring on the y. And then these two examples over here, these are just talking about if you had two variables, categorical variables. Those are going to be when you could do stack bar charts or side by side. It's just representing both of them, and both of them, the key is showing each group in different colors, but you can either put them side by side here or stack them on one another, whatever floats your boat. And then you have your two-way tables. This one's just talking about, once again, you do have two variables. So from this point down, we're talking about two variables. So here we have like gender, and then we have sport. So those are two categorical variables that we're looking at. So then you can kind of see the crossover for those, how many females, their favorite sport is football. You find that intersection there, so on and so forth. And then you always have your totals of the columns, and then your row totals too is always going to be there. And this is always going to be your sample size, the entire situation there. All right, risk and odds. So getting into probability, because I know everyone loves probability. So fun. Probability. So risk and odds are both describing the likelihood of an event, which kind of messes some people up, I think. But you do need to keep in mind they are talking about different things. They are interpreting the likelihood of an event in different ways. So risk is basically the same thing as probability. It's just saying the probability that an event will occur in general, so you use this equation here, number with the outcome divided by the total number of outcomes. But the difference between that and odds is the odds is comparing it to the event not happening, which is why our denominator is talking about the number without the outcome. So if we know that risk is if risk is a probability that something's occurring, that means that 1 minus risk is going to be whatever it is without the outcome, which is why we could also use this equation, only if you already have, if you're already like given the risk, that's when I would use this one. But if you're looking for odds, I wouldn't first calculate risk and then use this equation. I would probably just go straight to this one. It's the most straightforward. So same idea. So like I said, risk, just the probability that something will occur. Odds is the probability of an event happening versus it not happening. So just interpreting them in different ways, kind of giving us different information. All right, so let's talk about confidence intervals. So confidence intervals are basically, this is where we get a range of data. So remember, it's different than hypothesis tests where we kind of come to some sort of informed conclusion. Confidence intervals is giving us a range of data where we're kind of making inference of, in terms of that, where is, is our, we think that our population parameter is within this or whatever. So this is our general equation, our point estimate plus or minus 2 times our standard error. This 2 is if we're talking about a 95% confidence interval, like I wrote down there. So you're either going to have something like this, p hat plus or minus 2 times your standard error, which is, there's an equation for that, or you're going to have x bar. So remember, once again, this is what I'm saying, when those symbols come into play, you're only going to have p hat or x bar because this is your sample statistic. Your sample statistic is your point estimate, so you're going to use p hat or x bar. You're not using p or mu for this because it's a sample. So p hat or x bar, and then 2 times the standard error of your mean. So these are kind of the two equations you can have. And once again, I'm using 2 as a default for a 95% confidence interval. You guys probably remember that. So we'll talk a little bit about that in a second about, why we use 2. But this number technically can be anything, but it's dependent on, what percent confidence interval you have. That's how it would change. Standard error is just another way we'd say the standard deviation of our sampling distribution, because standard deviation usually is just, sigma, which is our, standard deviation of a proportion. But so yeah, remember, this is just a reminder that categorical goes with proportion, quantitative goes with means. So if you're trying to figure out if you should be doing a test for means or proportions, think about what type of variable is it. Is it like labels and names, or is it has some values associated with it? And then this is a side note just to keep in mind that when you increase your sample size, the confidence interval is going to be, I guess I'm going to say smaller, shorter, more narrow. And that makes sense because saying if you increase your sample size, more representative of the population, it's getting closer to the actual population size. So you can be more confident that your values are in a smaller area. So that's why it's going to decrease there. All right. And then, like I said, this is just describing why like confidence interval, like for example, why 95% confidence interval uses the multiplier as 2, because according to the empirical rule, 95% of the data lies between plus or minus 2 standard deviations of the mean. So if we're standardizing, if we were to standardize whatever like variable we had, we would go forth and do it this way and find it that no matter what it is, it's going to be 2 standard deviations away from that mean. So, sorry, I think my thing broke during my last review. It's okay. It's okay. So anyway, so yeah, that's our standard deviation. The standard deviation is 2, which is why we utilize that as our value. So, yep, living the dream over here. All right, let me clear it up. All right, and then we're going to finish up with hypothesis testing and then do some review questions. So we have here that when you're writing hypotheses, you're always going to have that there's no change. So it's always going to be an equal sign here. And then this doesn't work. Okay, so always going to have an equal sign. And then your that's not an equal sign. Okay. And then you're always going to have some sort of change over here for your alternative hypothesis. You're never going to have an equal sign here. Also, don't get tripped up. You can't have something like this because that still has like this part down here, and that means equal to. So that's saying there is a possibility that it is equal to, which isn't true. So that's how you would write hypotheses. So we'll kind of now go into interpreting the p-value that you get. So remember, if your p-value is greater than alpha, which we often say our p-value is, or alpha is often described as, or it's 0.05, so 5%. And remember, alpha is our probability of making a type 1 error, which we'll talk about in a little bit. But so yeah, our p-value is greater than alpha. We're going to fail to reject the null. We always assume that the null is true. So I always think your null is basically like your mother. You always assume that she's right. So, but you're trying to prove that she's wrong. But if you don't, you're just going to reject and say, is she right? Okay, so yeah, you can't conclude that there's any sort of change if your p-value is greater than alpha. And then, yeah, so that's what happens then. And then if your p-value is less than alpha, that's good because it's saying low probability that you made a type 1 error. We're going to reject that null, and we're going to say there's some sort of change, which means that it is in favor of that alternative hypothesis. Okay, and then these are errors. Like I said, these are the different types of errors you can make in a hypothesis test. So once again, type 1 error, rejecting the null when the null is actually true. So that's saying that you're saying that there is a change when there actually isn't a change. So that's like a false negative. And so yeah, denoted by alpha, so which is commonly set at 0.05, like I said. So and I wrote down here on this two-way table here, we just have a type 1 error is alpha. Then our type 2 error is going to be failing to reject the null when the null is actually false. So you're saying that there isn't a change when there is a change. False negative, yeah, I'm sorry, the first one's false positive, so which is denoted by beta. So this kind of shows a two-way table as to what decision you made versus what reality is, and then either if you made an error or a correct decision. And just a side note over here, power is 1 minus beta. Don't get tripped up on power. People freak out about that all the time, but it's just 1 minus beta. It's basically saying the probability of not making a type 2 error. So it's technically making a correct decision, but looking a different way. All right. So let's do a few review questions. So which of the following statements is correct about a parameter and a statistic associated with a repeated random sample of the same size from the same population? So read through these options and then go ahead and type what answer you think it is into the chat box, and then we will review this together. Okay, so remember that parameters, let's see if my little board thingy will work. Remember that parameters are fixed. Oh, heck yeah. All right, sorry, it's working now. So parameters are gonna be fixed, so they don't vary depending on the sample. That does not matter. So that's why, so A is not correct because it says values of a parameter will vary from sample to sample, not true. And then D says values of parameter will vary according to sample. No, already wrong. C says values of both a parameter and statistic. No, because a parameter doesn't. Parameter is, remember, parameter that's the measurement of a population, and this is going to be fixed. Remember, so this is independent, so it's not affected by our sample. The sample comes from this. Okay, so that's what changes. So our answer is B because statistics going to vary, but then this could also go on to say that a parameter doesn't vary. So does that make sense to you guys why the answer would be B? Because populations don't vary and they're consistent or whatever, fixed. Sweet beans. All right, let's see. Stop me at any time if you guys have questions, by the way, and like go ahead and like even if I'm talking, like let me know, because I used to kind of wait and like stare at you guys and wait for you guys to type, and I'm like, but then I decided to stop doing that because it was weird. So let's continue. For which of the following variables could we use a bar graph? So I'm just kind of going over what types of variables we use different representations for. So go ahead and let me know what you think the answer is for this one. Yay, amazing. Great job. You guys are geniuses. So yeah, our answer here is C. So the reason for this is, remember, bar graph is used for categorical variables, because remember, categorical, a cat is an animal. Meow, meow. So cat. So I got distracted. Anyway, so yeah, results from a poll of 300 people on what model car. So that is the model car is the only one on here that's a categorical variable. Grades on a final exam is quantitative. Dollar amount is quantitative. And then also height is also going to be quantitative. For being specific, this is going to be continuous. This is also going to be continuous. And then grades on a final exam. And also, actually, I want to clarify. Some people they said to me, they're like, "Wow, what if this is like letter grades?" Well, that is true. We could use bar graph for letter grades, but if this is like, you know, 100, 90, etc., technically, if this was talking about like if you only use like uh, variables of 5, like 100, 95, 90, whatever, that'd be discrete. But technically, if we're going from, if you can take like any percentage, that's going to be continuous as well. So your answer is C. So good job. All right. All right. A farmer is conducting a study concerning the heights of pigs on the farm, because that's so interesting. She takes a random sample of 50 research pigs, the best kind of pigs, and measures each individual's height in centimeters. So which of the following is appropriate for displaying his data? So go ahead and let me know what you think. It's a similar idea, trying to figure out what we display it as, and then we will go over it together. Okay, amazing. Good job, D. Amazing. So the reason for this one is because we're talking about one quantitative variable. So scatter plot would be for two quantitative, so that's why it's not that. And also the reason why it isn't C or A, because these are for categorical variables. So, and then scatter plot is two quantitative, but we're looking for one, so your answer is D. So good job. All right, we're trucking, y'all. All right, a kindergarten teacher wants to analyze the number of girls and boys in her class who like vanilla and chocolate ice cream. Which of the following is appropriate for displaying this data? As you can see, this is something that I feel like people struggle with remembering, so we do a lot of these, but go ahead and let me know what you think the answer is for this one. Amazing. Okay, so our answer here is C. So the reason why it's C, so remember, so you guys were right in thinking, so first categorical data because it's a category of flavor, so this is going to be categorical. So that's why it can't be a scatter plot or a dot plot. But the reason why it's going to be a two-way table and not a bar graph, because this is one categorical, because it's not like side by side or anything. Two-way table is two categorical. So here we have the flavor, and then also the gender. So that's why it's going to be two. So that's why you want to use a two-way table. So it would look something like male, female, and then I guess boys, girls, whatever. And then you want to go like chocolate, vanilla, and then boom. Then you'd have your totals. So two-way table. Good job. All right, so here's a hypothesis test for population proportion. So if we find that the p-value is 0.0 through 3, which of the following describes this data set and its conclusion completely with a significance level of 0.05. So let me know what you think about this answer, and then we will go over it together. Woohoo! Good job. Yes, so if we go through this one step by step, so we're looking for, if we're figuring out the tailed test, we look in the alternative hypothesis. Not equal to is going to be a two-tailed test, so that's why we know it's not B. And then mean or proportion, well, it's P, so I hope you guys understand it's a proportion. So we can X out C. And then based upon this p-value, so our p-value here, 0.033, is going to be less than alpha, which is 0.05, so 5%. So we are going to be able to reject the null hypothesis, and that's in favor of our alternative hypothesis. So the answer is D there, because we wouldn't fail to reject. That would be if our p-value was greater than alpha. That would be true. Good job. All right, one last question. Which of the following symbols cannot be used when writing a null and alternative hypothesis? So go ahead, read these through and let me know what you think. Amazing, good job, so proud. People always get this wrong, but yeah, so remember, if we have our population, excuse me, and our sample, we're talking about we want to use either P or mu, so population proportion, P or mu, and then sample is going to be P hat or X bar. But remember, we always want to use the population when we're writing the hypotheses. So that's why these ones would be the ones that we use, and we would not want to be using these two. So our answer is F, because those cannot be used. So good job. Amazing. All right, so you guys can obviously watch this recording back, plus the recordings from the rest of the semester. If there's a certain chapter that you guys want extra practice on, there's different review questions and more in-depth review on the different chapter responses and whatever. So if you haven't given me your Penn State email, please go ahead and type it in the chat box. If you have any other questions, let me know. There's a bunch of Q&As this week too, if you guys need help with that. And other than that, you guys are good to go for tonight.